All right, the time has finally arrived for the demo. So in this demo, I'm going to walk through a tutorial from start to finish, focusing on the use case setup and how to interpret the results. The part that we have here is called a material handler, and it's used to secure, lift, and position blocks of raw material into CNC machines. These blocks of material can be awkward to lift and position by hand and can damage the CNC machine if mishandled. So here in my hand, I'm holding down a scaled down version of this part. And you can imagine this block that's orange represents the block of raw material that I would put into the handler. So in practice, the material is loaded into the handler like this, and the machinist would hold the part up here. So the block of material is going to act as a force on this portion of the part. So just keep this visual in mind, because in a few minutes, I'm going to show you how to translate that into a use case and simulation. All right, let's get started. One of the first decisions you need to make is what print settings to use. Things like fill density and the number of wall layers are parameters that you can adjust that will affect part performance. What I like to do is start with the default Onyx settings, which I'm showing over here. This will give you a baseline on how the part is going to perform. So I'll enter the simulation view by clicking the simulation button, and we'll set up the use case. And the use case is really how the part interacts with other parts and how it is loaded. And to do this, I can select surfaces and define either an anchor or a load. Anchors are surfaces that are fixed and are constrained from moving, and load surfaces are surfaces where external forces are applied to the part. The raw material block, if you recall, was loaded into this U-shaped slot, and the operator grabs the handle on the left side of the part, just like I showed earlier with my scaled down demo part. When the operator lifts the part up, the raw material will exert a force on this highlighted surface here. So all I need to do is select that surface and select Create Feature Load. Now the orientation of the load is adjusted in the direction shown, which is the direction that the material block pushes on the surface when the operator is holding the part. And you'll notice that there are several tools for orienting the load. You can grab these red or green rings and adjust the arrow, or you can type in specific angles down here in the coordinates. So next I'll define the load magnitude, which is really just the maximum load that's expected for this part. In other words, the maximum weight of the raw material block. In this example, the maximum weight is 100 pounds, which is roughly 450 newtons. So I'll just type that in here in the force magnitude field. And my last step here is that I need to define the anchor. And for this part, that is where the operator will be holding it. So when the operator has loaded the block of material into the handler and is lifting it up, they will be holding on to this surface here. And that's where I'll create the anchor. The final step is to define the target safety factor and the max deflection, which are the performance requirements that define how strong and how stiff the part needs to be. The target safety factor is the desired minimum load factor allowed before yielding can occur in the part. That was a mouthful, so I'll say it one more time. The target safety factor is the desired minimum load factor allowed before yielding can occur in the part. The max deflection is the desired maximum displacement allowed for this part for this given load case. Here, the safety factor is 2, and the max deflection is 10 millimeters. This means that the part should withstand at least 2 times that design load before yielding can occur, and it should not deflect more than 10 millimeters. I will save the load case, and we're ready to run that validation. So when I click the validate button, a high fidelity model of the as printed part is created based on the information from how the part is sliced. This model takes a bit of time to construct and to solve. Typical run times here are about 30 seconds on the low end to about 5 minutes on the high end. So in the interest of time, I have already run the simulation. So if we fast forward in time 2 minutes, we will see the computed minimum safety factor and the maximum deflection, which are displayed on the part. And let's take a closer look at each one of those values. The minimum safety factor is 1.16. So what does that mean? it's telling us that the damage will begin to form in the part at a load factor of 1.16. So if you recall, our design load was 450 newtons. Now this means that damage will initiate at a load of 1.16 times 450 newtons, which is 522 newtons. Now, to be clear, the simulation is not predicting the ultimate load of the part. It's predicting the load when yielding of the material begins to occur, which is the onset of damage. And for part stiffness, the maximum deflection here is 15.9 millimeters. And these tooltips point to the locations on the part where these values occur and are color-coded, where red means the requirements were not met, and green would mean that they do meet the requirements. Here we see that the target safety factor is 2, but the computed value is only 1.16. And the target max deflection was 10 millimeters, but the computed value is 15.9 millimeters. So the part is not strong enough or stiff enough. Another feature that we have here is deformation visualization. So there's this displacement slider down here, which I can use to scale up or scale down the displacement. Right? And this is just a scale factor where 1x is true deformation, or how the part will deform under the given load case. And again, scale factors greater than 1 and less than 1 can be viewed. This tool is super handy for making sure that loads and anchors were set up properly. For example, if the part deformation was not as expected, it may be a sign that an error was made when defining the load direction. All right, so what do I do now? I can go back to the part view and adjust the print settings or the part orientation, or I can add fiber and run additional simulations, and I can explore how those specific changes affect the performance of the part. Or I can press the optimize button and let the software automatically adjust the print settings with the objectives of satisfying those performance requirements while minimizing print time and material usage. Both options have pros and cons. With manual adjustments, you have full control and you can explore things like part orientation and custom fiber placement, but it's more hands-on and it's going to require more attention. With optimization, you can explore many different part configurations and do so on autopilot, leaving you open to work on other tasks while the software does the heavy lifting. In the interest of reducing time to solution, it does not explore every single variable. So variables like the part orientation or custom fiber placement are not currently explored by the optimization. I want to do a quick manual iteration to demonstrate that workflow. And I'll return to the part view and select a version where I have manually placed fiber. And what I want to do is explore, what would happen if I added 6 concentric rings of carbon fiber to every layer in the part. And here is what that fiber pathing would look like. Right, there's a thick ring of fiber on the outer walls of the part, and this type of part falls into that category of intentionally overbuilding a part and playing it safe. So how do the simulation results look here? Okay, so I've already run this simulation. Again, that takes about 2 minutes to complete in real time. And we see that the safety factor has increased significantly to a value of 5. And the max deflection has gone down, all the way down to 1.3 millimeters. So by adding all of that fiber, we've made the part really strong and really stiff. But the part cost has increased, and we know it is stronger and stiffer than it needs to be. So we can explore how optimize can be used to identify a part that meets the requirements while keeping the cost to a minimum. Okay, so I'm going to return to the first validation result, which uses those default Onyx settings. And when I click optimize, the software will automatically generate alternate print configurations and run simulations in an attempt to find solutions that meet or exceed the strength and stiffness requirements while keeping print time and material usage to a minimum. Now, because it's running many simulations, the time to complete an optimization is longer than a single validation, typically between 20 minutes to about 2 hours on the high end. So I just press optimize, and I'm going to shift my attention to other tasks while it completes. After it completes, a table of solutions is going to be presented. So let's recall here, the goal is to find configurations that satisfy the requirements. while minimizing print time and material usage. The first tab here, labeled Current, shows the results for the settings used in the validation, which in this case are those default settings for Onyx. The Optimize tab shows the results for an Onyx-only part, and we see that this solution also does not meet the requirements. This means that the algorithm was unable to find an Onyx-only configuration that works. The Reinforce tab shows a solution that uses continuous fiber, or CFR. And here we see that both requirements are satisfied when fiber is used. All these tabs show the safety factor, the deflection, the print time, part mass, and the print cost for each configuration. And in addition, it's going to show you the difference in time, mass, and cost relative to the current configuration. So if I want to see the full list of solutions, I click the More Options tab, and the table pops up showing 5 different configurations. 1 with the current settings, 2 with just Onyx, 1 with isotropic fiber, and 1 with concentric fiber. The table contains detailed information for each solution. It's going to give you a quick idea of which print settings were adjusted, and it's going to allow you to compare part mass, time, cost between those different solutions. So the question now is, which solution should we use? In this example, I would go with isotropic fiber because it meets the strength and stiffness requirements, and it's the least expensive of the 2 fiber options. If I click the Apply button on the isotropic fiber solution, a new version of the part is going to be created with those settings. And what we can do is we can take a look at the internal view, which I've already generated here. And this internal view is going to show us where the fiber was placed. So we see that there are 2 fiber groups here, one at the top and one at the bottom. And each one of those fiber groups has 14 layers of carbon fiber in it. And my last step here is to just click Print. So that's it for the demo. I want to thank you for your time and attention. Have a good day.